All right. So I haven't had time to, obviously graded all the exams, or I've taken a little bit of a look at them. Kind of multiple choice portion looks kind of where I thought it would be. Grades don't look too bad, but until I get those graded, I won't really kind of talk too much about that. I'm hoping to have it all done by Monday for sure. There's a slight chance that maybe for this section I get it done by Friday, but I can't promise that. But I will start kind of working through those. And then once I have the grades, I'll talk a little bit about, maybe if they're a little bit lower, maybe there'll be a slight curve or something like that. And my GAs helped me kind of start grading through that third Excel assignment. So once those are both graded, I'll kind of get grades updated in terms of whatever your highest exam is. I'll make sure that's weighted the most. Whatever your lowest exam is, weighted less. And I'll kind of talk a little bit more about what that looks like on Canvas once all those grades are done for that second exam. Okay. I'll post an online quiz and a Learn Smart after today's class. So the online quiz should be pretty easy. It'll be related to what we talk about today, but that the Learn Smart will be kind of the next topic that we're going to look into. So we'll already go through a little bit of it today, but it's going to kind of set us up for a lot of other things that we're going to discuss, which is going to be really similar to what we were doing at the end of kind of the last exam, which is confidence intervals and hypothesis testing. Okay. So if you didn't like that, I apologize, but we got a little bit more that we're going to work through on it. Hopefully it starts making more sense as we kind of keep going through more examples, because not a lot is going to change from what we were doing before. Okay. Any questions for me before we get started here? We're good? Okay. Looks like we got 3 people here on Zoom, so I'm guessing a lot of people you probably want me to get this class over so we can get out and enjoy this weather, but we'll try to make it kind of quick here today. So before, we're working with one population. Right? So the kind of setup we're going to do throughout the next couple of weeks is looking at 2 population examples. We'll build confidence intervals. We'll do hypothesis testing. We'll have the same 3 scenarios. We're going to be looking at sample means when we know the population variance. We're going to be looking at proportions. And we're going to be looking at sample means when we only have a sample variance. So it's going to be the same 3 scenarios we had before, but now we're going to be looking for the difference between sample means, the difference between sample proportions, okay? And then finally, after we get through that, we'll have one more type of example that doesn't look like what we're doing with one population, which is matched pairs. But in fact, even though this is quite a bit different, it actually, I think, goes back to being something that's a little bit easier. So things will kind of progressively get a little bit harder, and then once we get here, we'll almost like go back to some stuff we talked about earlier, and it gets a little bit easier with these matched pairs. Okay. So I've got kind of the 3 motivating examples here, and don't write these numbers. I'm just gonna we'll work through these problems eventually. But here, maybe I've got econ and theater major starting salaries, and I want to know, can I build a 95% confidence interval for what the true difference is between those 2 different majors starting salaries? Maybe I've got 2 different years where I ask people, were they in favor of the Affordable Health Care Act or not? And then I want to say, okay, did views change between 2010 and 2011? Right? I might have drivers, their response time when they're texting and not texting. Are drivers' response times while they're texting slower? Right? These are the kind of questions I can ask. Well, really, I have 2 populations in all these examples: texters and non-texters, people in 2011 and 2010, econ majors, theater majors, right? So I've got really 2 different groups, 2 different populations that I'm sampling from, okay? So if we have 2 populations, what we know is that first population, we'll start using subscripts, so this is population 1, it has a true population mean. Even if I can't see it, it exists. It has a true population variance, right? And then if I take a sample from it, I'm going to have a sample mean of sample size n. Right? I then know for group 2, they might have their own mean. It could be different from group 1's. They have their own population variance, but I can take a sample from that group as well. I can then calculate my sample mean and sample size for that second sample I took from group 2. So, and actually I'll hold off on here. I'm going to go to the dot cam to kind of give you an idea about, we're then going to think, okay, I took both these 2 samples, right? I then want to look at, okay, what was the difference in those sample means that I saw. So one thing that we know is going to be true, if we go back to just one population examples, is that any group's variance of their sample means, is the original variance of the data we sampled from over my sample size. Let's just remember that for a second. So I'm going to try to give you a visual of why what I'm eventually going to tell you is true. So if I'm thinking about just the distribution of sample means, and maybe I've got group 1 here, I know that the sample means that I could see if I sampled from group 1 should be normally distributed around whatever that group's population mean is. I could then think about, I could also take a sample from group 2, right? And the distribution of those sample means should be normally distributed around whatever the population mean is for group 2. Okay? So if then I'm thinking about, all right, what will the distribution look like for the difference in those two sample means? Well, what's the most likely difference that I see? Well, the most likely value that I see from group 2 is going to be the true population mean or some value around it. The most likely outcomes I see for group 1 is the population mean or the values around it. So the most likely difference that I'll see is whatever the difference is between these two population means. So that's like the most likely difference will be whatever that true difference is between those population means. What's the next most likely difference? Well, maybe the difference between these values and the difference between these values, but they're a little bit less likely, right? And then what's the likelihood I see a difference that's that large? Oops, that large. Well, a lot less likely, right? So we want to think about in either direction, those differences just start to become less and less likely. What ends up being true is that the distribution of the difference in my sample means will be centered around the true population difference and kind of be normally distributed around that. I'm trying to kind of give you the vision here because that kind of makes sense, right? If these values are more likely for me to see, then those differences will be the most likely differences I see when I take that sample. And then the values are, way out here are very unlikely for me to see, so it's very unlikely I'll see these differences. Okay? What then ends up also, so we've got really what we're saying here is the mean for the difference in those sample means is just equal to whatever that true population difference is. And then the standard, well, I'll go the variance here for the difference in my sample means. And we could work through the mathematical proof. I'm not going to waste time on that. It's not interesting, and we don't have kind of not everyone's going to have the background for it. But what ends up being true, and it's kind of intuitive, is that the variance for the difference in my sample means is going to be the variance of each group's sample mean. So group 1 would have a sample, the sample means would have a variance of whatever the original variance was from group 1 divided by the sample size I took from group 1. And then I will add into that the variance that I had coming from group 2. Group 2's sample mean will have a variance of whatever the original population variance of the data I sampled from was divided by the sample size I took from group 2. Okay. So the distribution of my difference in sample means is centered around whatever the true population mean difference is. And the variance will just be the variance of each group, or each sample mean added together, right? Or the sum of them. Any questions up to this point? Anything that I did, or I don't know why I feel like the dot cam's a little blurry today. So if you're having trouble seeing anything that I'm writing, make sure you ask. Okay. So it kind of gives us this, I didn't put the standard deviation down, I guess, but right, if we wanted the standard deviation, we just take the square root of the variance there. So I now have the mean, and the statistic I'm interested in is the difference in sample means. Well, if I have the mean and the standard deviation of a statistic, I can start to do things like calculate z-scores, and we're going to be able to see we can build confidence intervals. So how do I build this confidence interval? Well, since I know it's normally distributed, I'm going to be able to get a confidence interval equation because I know the standard deviation for the difference, all right? But where does that kind of come from? So I'm going to build that equation for us. So it's on that slide, but I think I can make it make a little more sense. So we have, before what we were doing with one population examples looked like this. Okay? Well, the statistic we're now interested in is not just a sample mean, but we're interested in the difference in our sample means. All right? So this is kind of replacing this. We'll then add to get our upper bound, subtract to get our lower bound. Well, we know the population variances. Like this is kind of the setup, right? We have the population variance from each group. So because we're using population variances, we know that we can use that standard normal distribution. It's going to work the exact same way we're doing it before. We just want to know what that z-score is that gives me alpha over 2 on either side of my confidence interval. Or said differently, how many standard deviations away from that sample statistic I found do I need to go to the left and to the right? That's what that z-score represented. Well, if this is the number of standard deviations I need to go to the left and right, I then need to multiply that by not the standard deviation of my sample mean, right, but the standard deviation of the difference in my sample means, because that's now the statistic I'm interested in. If it's easier to think about as well, like really what we're doing here is we're kind of calculating this sample difference statistic, right? This is actually the statistic we're interested in is the difference. So here's that standard deviation for my sample difference as well. And we had that from the previous slide was just the square root of each group's population variance divided by that group's sample size that we took, okay? So that's, everything's really kind of similar to what I was doing before. It's just there's a few more moving parts, right? It's almost like I need two statistics here to calculate the statistic I'm really interested in, right? I need both sample means to find what that difference is, okay? And I'll work through these problems today, even more so than before. I think it's important, but also just, I shouldn't say important. I think it's easier and will be important maybe to understand the concepts a little bit. Here, instead of plugging this all in at one time, a lot of the times it's probably going to be helpful to calculate this intermediate value, which is just calculate the standard deviation of the difference first and then plug it in, right? Kind of like we had done before. But before there was fewer moving parts, so now it becomes even more helpful, right? All right, so I already kind of laid that out. So where are the steps going to be? Well, it looks like there's a lot going on here. It's basically the same thing we did before. It's just we have two sample means now, two population variances, and two sample sizes. Right? We identify the information we need. We're still going to be using alpha. We use alpha to find that z-score that gives us alpha over 2 on either side of the confidence interval. At that point, it's just a matter of plugging things in. I said you can add a step here if you want, which is to calculate that intermediate value, which is this guy here representing the standard deviation of that difference in sample means. But this will make a little more sense, probably if we work through an example, okay? So let's say I've got 40 econ alum and 50 theater alumni. I have a population variance, right, from each one of these groups. And I've got a sample size, a sample mean salary from each of these groups as well. So what would the 95% confidence interval be for the true difference between econ and theater majors starting salaries? So let me set this up here. I'm just going to write down what we have so I make sure I get all these numbers correct. So we're going to have two groups. We'll kind of call this sample size from econ, sample size from the theater majors. So we had what, 40 and 50? Okay. We then had the sample mean salary for econ majors, the sample mean salary for theater majors. This is what, 45,000. And I'll blow this up here in a second. I'm just writing these down so we have it all in one place. And then econ, theater, population variances were 9,000 and 6,000. The only other thing I need here is alpha. So the 95% confidence interval, what should my alpha be? Yeah, just the area outside of my interval in decimal form. So at 95% confidence interval, an alpha of 0.05, okay? So the next step is I need, if I think about this equation, one of the things I need is that z-score that gives me alpha over 2 on each side of my confidence interval. So if I've got an alpha of 0.05, alpha over 2 would be 0.025. So we're going to look it up the exact same way that we were before with one population examples. We'll go to that standard normal or that z table. All right. We're going to look up 0.025, go over and up. So negative 1.96, right? Negative 1.96. Okay. Now this is where we said the positive and negative are already built into our confidence interval equation. Okay. So I just need to use that absolute value, right? So my z-score for alpha over 2 in this case is 1.96, okay? Now from here, it's just really, I've got everything I need. It's just a matter of plugging everything in to this equation, okay? But if it were me, I would calculate this intermediate value first, right? So I would do something like, let's see if I can get this all to be on the same, there we go. So I would calculate, and actually this is going to be what? Econ and theater. So this would be what? The square root of each group's population variance. So 9,000 divided by the sample size from that group. So 9,000 over 40 and 6,000 over 50. Right. Forget what this ends up being. I think it's 18 something. So the square root of 9,000 divided by 40 plus 6,000 divided by 50, 18.57 approximately. Okay. Now from there, I can plug in my two starting salaries, plug in that z-score I found, and now I have something that represents that standard deviation of the difference in those sample means. Okay. So it'd be what? 45,000 minus 33,000. Got my z-score, got my standard deviation. Okay. Any questions? I know I'm kind of working between kind of two things here. Any questions about what, any of the values I plugged in? I know here it's the more general form of group 1 and group 2. I was just kind of using E and T here because we had a specific example. Okay. Now, one thing I want to point out, like if I gave you like a multiple choice question or something, or just a principle that's good to remember, I'm basing my confidence interval around whatever that sample difference that I found was. So here, my sample difference was 12,000. So my confidence interval should be centered around whatever that difference I found was between my sample means, or centered around 12,000. Okay. So if I actually go ahead and I add my margin of error to my upper bound, I subtract my margin of error to my lower bound. Oh, this isn't what I want. Right? We can get those values. It's just a matter of kind of plugging them into our calculator. Calculator there. Now, notice here on the slides, I did this all on one line. Didn't do the intermediate step. Makes it a little bit trickier, just more parentheses and things. But you can do it this way as well, and you'll be fine. Oh, thank you. Glad I didn't get too far into. Oh. Right, on the slides, I have it all entered in kind of on one line here. You can do it that way. Just makes it a little bit trickier when if you're don't have a real nice calculator. So I get this confidence interval that the true difference in starting salaries is somewhere between 11,960 and what, about 12,040. Okay. Now this one is not the most interesting because it's a pretty narrow I mean, shouldn't say it's not interesting. It's great if we can get a really narrow confidence interval because I can really zero down what this true difference is. I not only can say here, I know that the true difference between econ and theater starting salaries is positive. Those are the only values in that range. But I can also say that the true difference is at least $11,960, right? So, it allows us to start to really compare groups and make some big statements. And I think on one of the Excel assignments and then some of the stuff we did in class, I talked about if we had two different confidence intervals, if they overlapped, we couldn't say that one group was greater than the other, but if they didn't overlap, we could. Well, this is like that idea, but kind of wrapped all into one where we only need to find one confidence interval, right? So it makes it a little bit easier to kind of make those statements. Okay? Oh, any questions on anything here before we keep moving? We'll work through one more example here that I think will be helpful, and I can kind of point some things out that are a little more interesting about its confidence interval. Okay. All right. So my second example is, let's say we have two different states. Right. So I've got Indiana and Ohio, and I've got robbery rates, or is it robbery rates? Yeah, robbery rates for both the states from the same time period. So for each state, I've got 24 years or 24 observations, where my sample size for each group would be 24. I then find for Indiana, over that 24-year time period, their robbery rate was 109 per 100,000 people, and Ohio's was 163 per 100,000 people. I somehow have the population variance for each group. Not the most practical, or in application, it's not always very likely we'll have the population variance. But we have to start here and then eventually work to what happens if we only have the sample variance. So here we've got them given to us. So I want to build a 95% confidence interval for the difference between Indiana and Ohio robbery rates. Right? So first of all, I can start to think about, I need to make sure I get this order correct here. Right? So I want Indiana minus Ohio. So I'm just going to write down everything I was given, and then we'll kind of think a little bit more about how we go through and solve this. So we've got the same 24 years, or sample sizes of 24 for each state. Sample mean we found for Indiana and the sample mean we found for Ohio were what, 163 and 109. And then we have the variance, population variance that was given to us for each state, which is 175 and 497. So if I want to build a 95% confidence interval, what is that z-score that I'm going to need to plug into my confidence interval equation? Yeah, we just did a 95% confidence interval, and the z-score was 1.96. Well, if I want to do the same 95% confidence interval, alpha is still 0.05. Alpha divided by 2 is still 0.025. When I look it up in the table, I'm still going to have that z-score that gives me 0.025 in each tail be 1.96, right? So, the values we'll start seeing for these two population examples in terms of when we're building confidence intervals or even looking up critical values, they're going to look familiar. They're going to be the same values that when we were using for a one population example. So that part really hasn't changed at all. Okay. So one more thing before we start kind of working through this too much is, what was the actual sample difference I found here? So what is my confidence interval going to be based around? Right. So it's going to be that difference between Indiana and Ohio robbery rates. Right, that's what my confidence interval will be based around. So I've got what? 109 minus 163 here. So negative 54. So I know that my confidence interval should be centered around this value. Okay? I'm going to go a certain amount to the left and to the right of it. I know that z-score that gives me alpha over 2 here we found was 1.96. Right? So if I looked at those answers right away, I can rule out D because negative 54 isn't even in that confidence interval. Now the other ones, it looks like negative 54 would be smack dab in the middle of all of them. So A through C are all potential answers. Right? Any questions on that, what I'm saying there, or where we can rule out D? Because the sample difference I found was negative 54, so that has to be smack dab in the middle of the confidence interval. From there, like I said, I would calculate the intermediate step first. You don't have to, right? So we had that it was each group's population variance over that group's sample size, and then we add them together. But this represented the standard deviation for the difference in those two groups' sample mean. Okay? So I would go ahead and calculate this ahead of time. maybe down here or something. So, whoops. Just rewrite this. So I start plugging things in. I've got what? 175. So the square root of 175 over 24 plus 497 over 24. If I do this, well, there it is. Let's see, I get 175 divided by 24 plus 497 divided by 24, 5.29 approximately. So if I calculate the intermediate step, I can just go ahead and plug that value in here. Otherwise, I could have plugged all those numbers in here and did it all at one time. Any questions on anything that I just kind of went through there? Where are we at in time? Oh, okay, we're perfect. So I go ahead and I compute that. I get the true difference in crime rates or robbery rates, I guess, between Indiana and Ohio is between -64 and -43. Right? So that's interesting because if I think about what I've got now, so I've got this confidence interval. What was it? No, I already forgot. -64, -43, approximately. Right? So I know that the true difference, right? The true mean difference between Indiana and Ohio could be here, could be here, could be here, somewhere in this range with 95% confidence. But notice all these values are negative. So with 95% confidence, I can say that Indiana has lower crime or robbery rates in Ohio. In fact, I can say that at the very least, they have 43 fewer robbery rates per 100,000 people. Maybe as many as 64 fewer, right? So, that's interesting if my confidence interval for these two population examples only includes negative values or if it only included positive values, right? Because that way I can say that one of these states has lower or higher robbery rates. What's more problematic, I shouldn't say problematic, just not, I don't know, not as interesting or not interesting, not as useful, but it is what it is. If I get a confidence interval, let's say I found it went from what, 100 to 20, right? Well, I can't really make any statements because it could be that the true difference is, negative. It could be that the true difference is positive. So a negative difference means Indiana robbery rates are lower than Ohio. Positive difference means Indiana has more robbery rate or has a higher robbery rate than Ohio. But in fact, if my confidence interval kind of crosses over that zero threshold, one of the true values could be 0, which would mean the states have the same robbery rate, right? So anytime I have a confidence interval for these two population examples that crosses over 0, that has some negative and some positive values, I can't say anything because the true difference could be positive, could be negative, and it could in fact just be that they're the exact same and then that difference is 0. Okay? So to think about why maybe, I had a picture here. Yeah, I wanted to use this. So let's say, I don't know, this was Indiana and this is Ohio, right? Let's assume that these are the true population means. No, I didn't want to do that. What do I want to do? I want this to be Ohio and this to be Indiana. Let's say these are the true means, that the true mean robbery rate is higher in Indiana, right? Well, based off my confidence interval, it could be the case if I had that confidence interval that went from -100 to 20. The reason why, even though I see in my sample means that Indiana's sample mean was lower than the sample mean I found in Ohio, why maybe could it be that Indiana's mean is actually higher? Well, because the samples I could have seen, right, maybe for Indiana, I want to use a color that, right, maybe for Indiana, I see a sample mean down here, and for Ohio, I saw a sample mean way up here, right? The true means, population means is that Ohio's is larger, but based off my samples, I wouldn't think that. Now, what we're trying to do by building this confidence interval is say, well, look, yeah, but I know that if these were the true means, this would be very unlikely for me to see these sample means this far into the tail, right? But it still could be the case, right? I'm saying it with 95% confidence, so I am wrong 5% of the time, right? So this still could be the scenario, but based off the samples I found, they would have been so unlikely for me to see them that I'm okay saying with 95% confidence that the true values are between, whatever we found. I think it was negative 64 and negative 53, or 43. Okay. Any questions over this example or anything I kind of went through there? So really what we're looking for is hopefully we get a confidence interval that only has negative values or only has positive values. That way I can say like one group is greater than the other or one group is lower than the other. Okay? If it crosses over 0, I really can't say anything. All right, so if I can do confidence intervals, I can also do hypothesis testing. Okay? So if I want to do I can do it for the difference in means, difference in proportions. What we're going to do is call this difference. We're just going to use capital D to kind of notate that, right? There is some true difference. So this capital D, really what we're thinking about is here, right? That mean is what we're saying. The difference in our population mean, that's the true difference. We can't observe that, but we're going to assume that it's a certain value, right? We're going to have this assumed true difference, okay? Usually, we're going to use 0. Now, I'll show you examples in class when it's not 0. When it comes to connect problems or when it comes to like a final exam, I'll only use examples where that assumed true difference is 0. Because we'll end up seeing that it usually is anyways. But we can use non-zero values. But for us, we're going to use 0 here. Well, the types of tests we can do are exactly the same. This is the exact same thing I showed you for the population mean. It's just now I'm looking at the true population difference. I'm using an assumed true difference value. We said most often 0 here. I've still got my left and right-tailed tests, my one-sided tests. I've still got my two-tailed or not equal to tests down here. And things work exactly the same as they did before, all right? So we're going to be getting more and more practice with these hypothesis testing examples. And really everything's going to be the same with like a few small exceptions. So when we're thinking about the steps, identifying the null alternative is the first thing we have to do. We have a left, right, or two-tailed test, right? Now, it might be a little bit more tricky. We'll work through one example today and I'll kind of try to talk you through it. It is a little bit trickier to identify the null alternative. We then need to use alpha, and we can use alpha to find critical values, right? Or if we wanted to find the p-value, right? And once we have those critical values, we need to compare it to the test statistic. Or we could find that test statistic and then use the test statistic to find a p-value, right? We can then use, if the test statistic's in the rejection region or if the p-value is less than alpha, we reject. So the steps are exactly the same as they were before. Nothing's changed here. This is the exact same slide I showed you with the one population example. Okay. The one difference is, so everything's gonna be the exact same, right? We find the p-value, come on. There it goes. We find the p-value the exact same way we did when we were using population means. Critical values are gonna be the exact same as they were with one population example. Like nothing has changed with the critical values of the p, or kind of how we find the p-values. The one thing that has changed is the test statistic that we're going to use. So I'm going to show you how we get to this point. So before, what we were doing with test statistics, that's out of the way, we had a what? My test statistic when I knew the population variance was take my sample mean, subtract the assumed true mean, and then divide by the standard deviation of my sample means. That was my test statistical equation. It's the exact same format when I'm looking at the difference in sample means. It's just that I'm no longer interested in just one sample mean. The statistic I'm interested in is the difference in between two population sample means. So my statistic has changed. Remember we said we can think about this as kind of the sample difference that I found, right? The difference that I found in my sample means. So now I'm no longer interested in just one sample mean, I'm interested in the difference. So I can't subtract the assumed true mean, I'm going to subtract the assumed true difference. We said more often than not, this is 0. So usually this kind of just drops out, it actually makes it a little bit easier. And then I'll divide by, not the standard deviation of a sample mean. Here I'm going to be dividing by the standard deviation of the statistic I'm interested in, which is the difference in these sample means, right? I said I can think about this as kind of the sample difference, right? Well, just like with confidence intervals, we had an equation for this. We knew that the variance for the difference in sample means is just each sample mean distribution's variance added together. So that's the exact same thing we're going to use here. Same thing that we had with our confidence interval. So the square root of each group's population variance divided by its sample size, and then add them together. Okay? So that's where that test statistic equation comes from. It's really the same setup. Sample statistic I'm interested in, subtract the assumed true value of that statistic. Divide by the standard deviation of whatever statistic I'm interested in. Okay? Once I have this test statistic, though, finding the p-value, if it's a left-tailed test, it's the area to the left, right-tailed test, area to the right, two-tailed test, find the area of the tail, multiply by 2. All of those principles, nothing there has changed at all. So like the procedure of what we're doing hasn't changed, and the idea of what we're doing hasn't changed. It's just we're looking at a different statistic, right? Similar to the fact that when I was looking at my test statistic equations, the denominator was a little bit different for my sample proportion compared to my sample mean. Well, that was because I'm looking at a different statistic. So the standard deviation of that sample statistic might be a little different, right? The standard deviation of this sample statistic is just a little bit easier than the standard deviation of this sample statistic. But it's still the same idea of how we're finding these Z statistics or test statistics here. Any questions over anything here? I want to show you kind of where that comes from, but now that we kind of have this, we could work through an example, right? So I want to not work through an entire example today. We'll get out of here a little bit early, but I do want to at least talk through a little bit about identifying the null and alternative hypothesis. So let's say I've got this example where I've got, I don't know, some newer years, right, 1990 to 2011, where I've got the number of tropical storms on average across those years was 15.5 per year. I then have this older time frame, 32 years, when I found the average number of tropical storms then was only 9.7. So I want the true difference between kind of my group 1 and group 2, or the difference between the newer and the older time period. And I want to test for whether or not tropical storms have increased. Okay? So if I want to know if tropical storms have increased, it gets a little bit trickier to identify my null and alternative hypothesis, because what am I really saying there? What I'm saying is, I'm going to write this in the middle. What I'm really wanting to test for is that mean from that newer time period, 2011 I think was the last year, if tropical storms have increased, that would mean the new mean is greater than the older time period's mean, all right? Everybody with me on that? If tropical storms have increased, the newer year's mean should be greater than the older year's mean. Well, but this isn't written in, I don't have an assumed true difference here. What you kind of do is just hiding, okay? So if I'm thinking about the difference is between the new time period and the old time period, right? I could actually rearrange my alternative hypothesis just a little bit. If I subtract this from both sides, what I'd be left with is greater than 0, right? If I subtract that mean from both sides. So really what I'm saying, if tropical storms increase, what I'm really saying is that difference greater than 0, right? That's what I want to test for. I then assume the opposite is true, which is that it's less than or equal to 0, right? So really my assumed true difference that I'll be kind of testing against here is 0. Right? And this is why quite often we'll use that assumed true difference of 0, because the way that we do want to test for things is, have tropical storms increased, right? Have they decreased? Are they different from each other? We're really just saying, like, is the difference greater than 0? Is it less than 0? Or is it anything other than 0, right? But in identifying the null alternative, it's a little bit trickier because, like, the way we say it in English is like, have they increased? And I think when we say have they increased, we think about this. But what this is really saying is the difference has to be greater than 0. Okay? So I'll walk through a lot more examples like this, and I'll always kind of write it out mathematically what matches up with the English, and then how could we like rearrange that so that we have a difference kind of in that null alternative hypothesis. Okay. So we'd have a greater than sign in the alternative hypothesis here. So we'd have a right tail test. Okay. We could then use those values, right? If I had a right tail test, my critical values are going to be positive on the right side of the distribution. I've got population variances somehow in this example, right? They were given to me. So I can use the standard normal distribution. And really, once I have all that, the procedure is exactly the same as what we did with one population examples, with the exception of, okay, the test statistic equation is probably arguably a little bit harder, right? There's a few more moving parts, okay? So this is, we didn't get quite as, or we ran out of a little time in the last section, so I didn't do it quite as efficiently. But here is, we kind of have this example that we'll pick back up on Friday. So kind of the way that we'll start moving through this class, I've got these, 3 different types of problems, right? So the first one today was sample means, where we know the population variance. We did confidence intervals. We're starting hypothesis testing. We'll work through more hypothesis testing on Friday. We'll then I'll show you how to use it in Excel. So we didn't spend a lot of time in Excel with one population examples. There was a reason for that. We'll spend a lot more time with these 2 population examples. Once I do that in Excel on Friday, if we have time, we'll then start looking at, okay, what if I want to compare 2 population proportions? We'll do confidence intervals, hypothesis testing, Excel examples. Then I'm going to do sample means with sample variances, confidence intervals, hypothesis testing, Excel examples. So I have an Excel file up there about 2 population hypothesis testing. We're going to be going through it a little bit slower because I'm breaking it down into parts instead of doing it all at one time. And I think that'll be good because that way you see me do more in Excel, kind of like a little bit every single class period. Okay. So that's where we'll pick up. Make sure you get onto that online quiz before we meet on Friday. Also, that Learn Smart, I'll probably have the due date set to be Monday. Okay. So you've got a little bit more time to kind of get on. Should take 10, 15 minutes to get that done, get the easy points. Other than that, enjoy the nice weather, and I will see you guys on Friday.